What's up, everybody? It's Dan from SageMathTutoring.com, and I have, it was originally going to be 5, but I decided to do 6 calculus problems based on a review sheet that one of my students is working through so as to prep for a test tomorrow. So once again, 6 problems, all stuff related to integrals, antiderivatives, and these are some problems that she had some questions about that I decided to make a video for so she can look at it later. Let's look at this first one. Well, first of all, basically what I'm going to do with these, partly in the name of like moving relatively quickly, I'm just going to go through it. I'm not really going to teach the concept as much as I'm just going to think out loud. I think with the last 2 problems, I'm going to teach the concept a little bit more, but for these, I'm going to think out loud because a lot of the stuff my student already knows, but she just needs to be pointed at least somewhat in the right direction. So when it comes to this amazing integral, obviously there's an absolute value, which is kind of annoying. However, the bottom line is it's 2 terms separated by subtraction. So anytime you have 2 terms separated by addition or subtraction, you can split the symbol up there. So it becomes x, and then it's going to become minus 2 absolute value of x dx. Okay, now I'll preserve these. Now, this is going to be very straightforward, whereas this is going to be a little bit more complicated. Now, my student at home, I think, recognizes that this 2 could go on the outside, so I'm going to get that over with now. We're going to have this scenario with the 2 on the outside. Okay. And we also kind of see that it goes from -1 up to 2, so it goes from least to greatest. We're not going to have to flip anything or do anything interesting there. Now, let's see what we have going on. Let's take care of this because that's pretty easy, right? That is just going to become x squared using the power rule over 2 with the 2 and -1 there. But then it's really this part here that we're going to have to contend with now. So we're going to have 2. And the question is, what is going on with the absolute value symbol situation? Well, there's really 2 ways of approaching it. Number 1, you could recognize that the function y equals absolute value of x, it's kind of like this v, right? And like this part has a slope of 1 over 1. This part has a slope of -1 over 1. And I know that because the invisible coefficient in front of the absolute value symbols is 1, okay, 1 over 1. So that's a sign that it's like this perfect diagonal situation, a perfect diagonal situation here. Now, one way of going about this is to consider the absolute value function and to actually ask yourself, well, what is the area under the curve from 2 to 1? So that's actually not a bad way to go. We've got 1, 2 right there, and we've got a -1 right there. And we could always be like, okay, well, that's a triangle right there. And the area of this part is most definitely going to be 1/2. No question about it. That is 1/2. The area, this area is going to be 1/2 base times height, and the base is 2. The height would also be 2. It's not drawn to scale. And that's going to turn out to be 2. Okay. So the area of this absolute value thing from -1 to 2 would be 1/2 plus 2. So the area would be 2.5. But we would have to remember that it's going to be 2 times that, right? So we have -2 times that area under the curve. So -2 times 2.5 is -5. Okay, so that's one way of going about this whole thing. We could recognize that, oh, okay, it's just -5. It's just -5. So I'm actually going to get rid of that 2, and we're going to put a 5 there, okay? And, you know, it's -5, -5. And then you could work that out and then just subtract 5, okay? So that's one way of going about dealing with the absolute value symbol. Consider the V shape, find the area under the curve there or under the V. In that case, when it goes from -1 to 2, use these triangles. That turned out to be 2.5. It's going to be -2 times 2.5, which is just -5. Okay. Don't forget to multiply -2 times whatever that area is. Now, that is most definitely one way of going about it. That is a way that I don't think the teacher would mind based on the rest of the review sheet. There certainly does seem to be some trickery when it comes to the review sheet. So I don't think that should be a problem. I would like to present, however, another way of looking at things. And that would be to consider a different approach when it comes to the absolute value scenario. All right, different approach. And the other approach would be to recognize that the absolute value of x, well, that really is two scenarios. It's going to equal positive x when x, at least in this case, is greater than or equal to 0, and it's going to equal negative x when x is less than 0. So, in a way, we have two derivatives to deal with. We have the derivative, or the antiderivative, I should say, that pertains to values of x greater than 0. We have the antiderivative that pertains to the values of x that are less than 0. Now we have some values of x that are less than 0 because this goes from -1 up to 2. So one way of thinking about it is that, sure, we got all this right here in red. We could do that on the next line, but let's kind of take a look at this. We're going to have -2, of course, and we're going to do some brackets here. It's going to be times the derivative of, we'll say negative x, I'm going to put the negative out there, negative x dx, when x is less than 0. So that's going to be from -1 to 0, right? Because it goes from -1 all the way up to 2, but we want negative x when it's less than 0. So it's going to go from -1 to 0, and then we're going to be adding the derivative from 0 to 2, and in that case, it's positive numbers, and it's going to be x. So hopefully for my student at home, that makes sense. That is certainly a valid way of going about this. Now, when we proceed, I like to just kind of focus on one step at a time. Now we have a bunch of stuff going on here. We got a lot of action over here. Some mathematicians would insist upon doing this maybe off to the side, doing this off to the side. I'm just going to go line by line. I'm going to do one extra thing every line. Okay, that's the way I like to do things. So as it pertains to this scenario, I think we can all agree. I'm going to keep that in purple. We're going to keep this in purple. So for the purple situation, we're going to have 2 squared all over 2 minus -1 squared all over 2. Now that is most definitely something, and we will figure out what that is soon. In the meantime, we have 2 times this bracket. Well, what's going on over here? Well, certainly we have a negative. So there's a negative right there. And then it's going to be negative, well, that's my half bracket, half parentheses. It's going to be negative x squared raised to the x raised to the second power all over 2. And that would be such that we have a -1 down here and a 0. So this is another way of representing the fact that you're going to be substituting -1 and 0 in. You could just put them here on the corners of the brackets. Now that will be plus this other situation where it would be also x squared over 2 with the, in this case, 0 and 2 there. Okay. Now I have this whole thing in brackets, so I'm going to make sure that that's represented at the end. Okay. Once again, kind of a crazy situation. I think one way of preventing yourself from being overwhelmed is realizing that you just do one more thing, bring it a little bit closer to the answer, and then let it go. Then you can focus on the next move. Looking at the purple part, what's that going to be? That's going to be 4 over 2, which is 2. and that's going to be, negative 1 squared is positive 1, right? So that's going to be a 1/2 right here. So it's going to be 2 minus 1/2. Well, 2 minus 1/2 is 1.5, also known as 3/2. So I'm just going to represent it that way. In the meantime, we still have this 2 on the outside, and we will have, well, it's going to be negative, so we're going to stick a negative out front, and let's kind of work this out. This is going to turn into 0 squared over 2 minus negative 1 squared over 2, which I am going to worry about on the next line. Let's focus on this one. We're going to have plus, and let's do brackets, keep it organized. It would be 2 squared over 2 minus 0 squared over 2, which I will worry about on the next line. So we will continue. I know that this is a bit of a doozy, a little bit crazy, not the funnest problem of all time. And in fact, some of you are probably wondering, you know, I'd rather just graph it and graph the triangles. Because we already know what this is going to be, right? We already figured it out. But again, I don't know. Maybe this is, the professor would insist that you do it this way. I don't know. But let's continue. So we have minus 2, brackets. Well, let's take a look at this. It's going to be negative something. Well, what is that something? It's going to be 0. Now remember, negative 1 squared is positive 1, so that's going to be 1/2. So it's going to be 0 minus 1/2. So that will most definitely be a negative 1/2 on the inside, which we will worry about soon. Looking at this, we are going to have, looks like that's going to be a 4/2, which is 2 minus 0. So that is straight up 2. I don't need brackets in this case. It's just a 2. Focusing now on the next line. We still have our purple 3/2 minding its own business. We still have the 2 on the outside. We're going to have negative 1/2, aka 1/2. And then we're going to have plus 2. So that is most definitely going to be plus 2. And lo and behold, wow, it's just going to be negative 5. So once again, for my student at home, listen, if you want to do the triangle, graphy, V-shape, absolute value function thing, you know, feel free. Feel free. This is 2.5, aka, that's actually 5/2. Bringing it up here because it's starting to get too small. We're going to have 3/2 minus what? 5. Minus 5. Now, what is 5? 5 is really 10/2, right? So, well, it's really just 3/2 minus 10/2. And that's negative 7/2. That is the answer. That's how you do number 26. Now, for the record, I just checked out my student's answer sheet. My student's answer sheet says negative 3.5, but just know that negative 3.5 is this. All right, so that's the answer. Okay, for problem number 28, as far as I could tell, this is probably a good candidate for U substitution. Something like that. I think so. So let's take a look. U could equal 2 theta. Therefore, du is going to be 2 theta, or 2 rather, pardon me, 2 d theta. Now, in case my student at home is wondering, what? D theta? What? Just recognize that if u was equal to 2x, well, wouldn't du be 2 dx? It would, right? It's just that instead of x, we're using theta. Now, the way that my student and I just discussed as it relates to what to do from here is something that might be different than what some teachers teach, but we're going to do it this way because it's actually less confusing, probably, to do it the following way. What we could do here is then do this extra move where we actually solve for d theta. And then that's going to become, I think you would agree, du over 2. All right. Now, it's really these pieces of information that we're now going to be substituting in. Anytime we see a 2 theta, we can now replace it with a u. It's official. Anytime we see a d theta, we can now replace that with a du over 2. All right. Now, that's not a bad way to go. So we're going to have pi over 8, 0. And now it's official. We got secant of u times tan of u, which is a lot better. And then instead of d theta, we're going to write du over 2. Now, this 2 is really, you can think of it as being just under the du, but really, since it's nothing but multiplication up here, the 2 is kind of underneath everything. You can think of it there being one big fraction line with a 2 underneath. And the bottom line is there's an invisible 1 above the 2. It's really just a 1/2. So what we could do is we could take that 2 and put it on the outside as 1/2 on the outside. Okay? And we still have everything else. And we still have this. Okay? Now that is a normal situation. We had double angles over here, which is kind of annoying. But this is a more normal situation where it's just secant of something times tan of something. Now, my student at home hopefully has a reference guide when it comes to like the integrals with trig function things. There is something on a reference guide, on most reference guides, that would tell you that secant of x times tan of x dx is going to equal secant of x plus c. Okay? Which is kind of interesting. These two things, when you do the integral, it actually just turns out to be this. Okay? Now, this is, for indefinite, whereas we have a definite integral situation. Indefinite would have you place the c, so we're not going to be doing a c over here. But we do know that it's going to be secant, so that's good. So, great. We still have the 1/2 on the outside. And now we can just switch to brackets, right? It's literally just going to be secant of u. And then up in the top corner, I'm going to put my pi over 8, right? Pi over 8. I got my 0. And now we're ready for the next step. Now, it's not u that we're working with. It's 2 theta. So I would say on the next line, we could substitute 2 theta in. We'll do it in a slightly different color. We're going to keep this red, though, just to keep our eye on it. So it's going to be secant 2 theta with this scenario going on. Okay. Now, let's wrap this up, and we're going to bring this here. We have 1/2 times this whole situation. It's going to be secant of 2 times pi over 8 minus secant of 2 times 0, okay? And working through it, we would have secant of, that's going to be pi over 4. Now I'm using these little parentheses just to kind of, I like parentheses, just I feel like it separates things out. And then clearly this is going to be secant of 0. Now the question is, all right, well, what is the secant of pi over 4? What's the secant of 0? Well, let's think about it. There's really 3 triangles you need to familiarize yourself with when it comes to figuring out like trig functions and so on. 3 main triangles at least are the 30, 60, 90, where that's 30, that's 60, and obviously the bottom right one is 90. You also have the 45, 45, 90. All right. And you also have the 30, 60, 90 only positioned in this fashion. Okay. Now, typically when you're learning trig stuff, let me just put it this way. You want the hypotenuse to be 1 unit long. all right, because usually we're working off the unit circle. Now, if my student at home doesn't understand that, don't worry about it. Just know that the hypotenuse is going to be 1. Okay, just remember that. Now, let's also remember a couple things. 30 degrees is really pi over 6. Okay, we're only going to pay attention to the angles here. 45 degrees is really pi over 2. Actually, not pi over 2, pardon me, pi over 4. 60 degrees is really pi over 3. Now, when I say pi over 6, pi over 4, pi over 3, I mean pi over 6 radians, pi over 4 radians, and pi over 3 radians. I should have mentioned that. Radians are just another way of measuring angles. 30 degrees is equal to pi over 6 radians. 45 degrees is equal to pi over 4 radians. 60 degrees is equal to pi over 3 radians. Now, for my student at home, if you want to write down these triangles, it's not the worst idea in the world. Okay. Now, as you may recall, in a 30, 60, 90 triangle, the short leg is always going to be half the hypotenuse. So that short leg is going to be 1/2. Okay. The long leg is always going to be whatever that is times radical 3. This long leg is going to be whatever the short leg is times radical 3. So the long leg, I'll write it in yellow, is going to be radical 3 over 2. All right. In fact, I'll write this in yellow too. As it pertains to the 45, 45, 90, it is worth noting that the legs are the same length, and it's going to be radical 2 over 2. When it comes to the 30, 60, 90 here, well, we have the 60 over here and the 30 up here this time, so that means that the short leg is down here. That's going to be 1/2, and I'll write that a little better, 1/2, and that's going to be radical 3 over 2. Now, this is really going to come in handy when you're figuring out the secant of pi over 4. I mean, that's what I'm doing here. And the secant of 0, to be perfectly honest. Now, let's also remember that sine of theta is equal to opposite over hypotenuse. Cosine of theta is equal to adjacent over hypotenuse. Tan of theta is equal to opposite over adjacent. Let's also remember that the reciprocal function of tangent is cotangent. So since it's a reciprocal, it's going to be A over O. Now, this is the part that's a little bit harder to remember. The reciprocal of cosine is secant, and the reciprocal of sine is cosecant. I actually always remember that it's kind of the opposite of what you would think. You would think that maybe the reciprocal of cosine is cosecant because it has co in it. But remember, cosecant belongs to sine. So the reciprocal of the sine is cosecant theta. And that means that it's going to be h over O. And the reciprocal function of cosine is secant theta, and that's going to be h over A. All right? Now, in case you're wondering where all this came from, at least this part, well, that is SOHCAHTOA. Okay? Where the sine is opposite over hypotenuse, the cosine is adjacent over hypotenuse, the tangent is opposite over adjacent. Once you have this written down, that becomes easy because that's easy to remember. Then this one, you'd have to do the switcheroo and remember that it's reciprocal functions here. Now, that's a lot of information. That's a lot of information right there. So you might be wondering, okay, thanks for confusing me. Why do I need to know this? Well, the reason is because once you understand this, or if you have the reference in front of you and you're staring at it, it might actually be easy to understand what secant of pi over 4 is. The secant of pi over 4. Well, what is pi over 4? Pi over 4 is 45 degrees. There it is. Right? Pi over 4 radians. 45 degrees. What's the secant? Secant is hypotenuse over adjacent. So we have the 45 degrees here. The hypotenuse is 1, and the adjacent is radical 2 over 2. So that's going to be 1 over radical 2 over 2, which we're going to worry about later. Now we have the secant of 0. Okay, secant of 0. Well, that's a tough one. I mean, 0 degrees or 0 radians. Well, what I could tell you for sure is that the cosine of 0 degrees is 1. Okay, the cosine of 0 degrees is 1. Turns out that these triangles are not particularly helpful when it comes to understanding the value of 0. Maybe a better way of recognizing what's going on with 0 degrees is to imagine the unit circle. This is a circle that has a radius of 1. Therefore, this point right here is 1, 0. This point right here is 0, 1. This point right here is negative 1, 0. This point right here is 0, negative 1. And you can imagine that. And angles always start here. So if you were to consider 90 degrees, it would start there, but then it would open and end right there, and that would be 90 degrees. But understanding that this yellow part is where the angle begins. Okay, if you open up 90 degrees, it opens up counterclockwise and lands there. Now 0 degrees is just this. It's like this flat thing, right? Now the cosine of an angle is always associated with the x-coordinate. So the cosine of 0 is 1. Now, the secant is the reciprocal function of that. So in other words, the cosine of the angle is 1. So what's 1 flipped upside down? Well, it would just be 1, right? Because 1 is 1 over 1. So if you flip 1 over 1 upside down, well, it would be 1 over 1. So it turns out that secant of 0 is 1 flipped upside down, which turns out to just be 1. And the reason that the secant of 0 is 1 flipped upside down is because secant is cosine flipped upside down, and cosine of 0 is 1. All right, so hopefully that makes sense. It would require a full-blown trig review if it doesn't make sense, and I don't really want to go there right now. Anytime you have 1 over a fraction, you could just take the fraction, flip it upside down. So that just becomes 2 over radical 2. And that's going to be minus 1. Now, mathematicians typically do not like it when you have a radical in the denominator, so we got to multiply the top and bottom by radical 2 over 2. Radical 2 over 2, and what that would result in is we're still going to have that 1/2 on the outside, but then this is going to become, it would ultimately become radical 2. Okay. And it's minus 1. Now, in case you're wondering, how did 2 over radical 2 become radical 2? Well, if it was 2 over radical 2, and we decided to get rid of the radical on the bottom, we could multiply the top and bottom by the radical. Well, up top, it's going to be 2 radical 2. Down below, it's just going to be 2. And then these 2's would cancel, and it would leave us with just radical 2, which is right there. All right. So in other words, this 2 radical 2 just becomes radical 2. So that is that. And one way of representing the answer, the final answer, could just be radical 2 minus 1 all over 2. That is certainly one way of doing it, and I think that's a way the teacher would not mind. This one looks scary, but it's really not that bad. This is a very straightforward U substitution problem where U would equal the stuff that's inside the parentheses, okay? Because, now they might be wondering, well, how did I know that, right? Why can't U just be X? Well, first of all, U is never X. If U equaled X, then there'd be no point in U substitution. You just go with X, okay? Now, you could say maybe U could be X squared. That's something to think about. We could try that. But my view is that, I don't know, I feel like it would be cool if we could have a U to the 5th. So I'm just going to start there. So U equals 1 plus 2x cubed. And when you take the derivative, it's going to be 6x squared dx. Okay. Obviously, power rule, multiply 3 times 2. Drop the exponent down by 1, so it becomes 2. At this point, the way that we're going about things is to solve for dx. So it's going to be du over 6x squared. And it is these pieces of information that we're now going to be using when we substitute back in. Now, the x squared is just hanging out, minding its own business. There it is. But clearly this is u now, right? So that's u to the 5th. Now dx, according to our setup here, is du over 6x squared. So instead of writing dx, I'm going to write du over 6x squared. Now, the good news is the x squareds cancel. In fact, that's what you want. That's how you know that you're on the right track. What you don't want is a mix of u and x's together. That's like an impossible situation, all right? Or certainly a situation that's not helpful. So we have x squareds canceling. We do have the 6 on the bottom. Now let's think about that. There's an invisible 1 up here. I mean, it's nothing but multiplication going on up here. There's an invisible 1 up here. So a 1/6 can get out of this whole thing. I'm going to leave that off to the side like that. And what are we left with? We are left with u to the 5th du, okay, with 1/6 out front. So pretty straightforward, I would say. And then at that point, you could recognize, okay, fine. It's going to be 1/6 out front times u to the 6th over 6. We still have these bounds here. And continuing on in that very same fashion, it's going to be a matter of substituting 1 plus 2x cubed in for u. So really it is 1 plus 2x cubed raised to the 6. You don't want to forget that part. And then we still have these bounds here. Now, it could be the case that you're looking at this and freaking out because, like, when's the last time you raised something to the 6th power? Probably not, probably long ago or never, right? But you just trust the process, right? Trust the process. Sometimes these numbers, when you plug them in, it results in very easy values. So we have 1/6. And, okay, so we're going to begin the process of actually plugging in those numbers. Speaking of which, we're going to do this part in our head. You're going to find a lot of times, not always, but a lot of times you could actually do this part in your head. So if we plugged 1 in for x cubed, it would be 1 plus 2 times 1 cubed. Well, 1 cubed is just 1. 1 cubed is just 1. 1 times 2 is 2. 2 plus 1 is 3. So it's going to be 3 in here raised to the 6th power. So it's going to be 3 raised to the 6th power all over 6. Now, we're going to be subtracting the whole scenario where we plug in 0 for x. Now, if we plug in 0 for x, it's going to be 0 cubed, which is just 0. 2 times 0 is 0. 1 plus 0 is 1, so that's going to be 1 over 6. So we have 1/6 right there. So we are done with the substitution aspect of it. Moving forward, we have 1/6 right there. Now, 3 to the 6, what is that? The way I like to do these things sometimes is to recognize that 3 to the 6 is really a string of 6 3's being multiplied together. Well, that's definitely 27. That is also 27, and then you could just do 27 times 27, okay, and that's going to be 729. Now, it could be argued that it would have taken just the same amount of time, if not less, to just plug 3 to the 6 in your calculator, so that's fine. But 729, that's it, 729. So we're going to have 729 over 6 minus 1/6. Now, we already have the common denominator we're looking for, so I say let's take advantage of it and immediately subtract those fractions. So it's going to be 728 over 6. Now, that will be 728 over 36, which reduces to 182 over 9. So that is the answer. Okay, hopefully that makes sense. Yeah. Even though it was complicated at moments, it was still a somewhat straightforward problem. It's possible you may have made a mistake by calling x squared u, and then you would have quickly seen that upon substituting everything back in, you would not have gotten the cancellations that you need, and you still would have had some x's hanging out. So it turned out that the proper substitution for u is 1 plus 2x cubed. Okay, so 43, in my opinion, is an example of a somewhat intimidating problem because this is just a big mess down here. First of all, it's trig functions. Second of all, one of them is squared. That makes things even worse. And worst of all, you have a square root of something that's not even a trig function. It's 1 plus a trig function. So that is kind of scary if you're not used to, I would say if you're not used to simply trusting the process, it's going to be scary. Now, what is the process? Well, the process would be to, in this case, play around with U substitution. There's no obvious solution to any of this. You don't see any of this on your reference guide when you look at your trigonometric derivative / integral reference guide. There's no double angle formula action going on here, so you can't do any like conversions right out the gate. So you are sort of stuck with having to simply experiment with U substitution. Now, I would suggest that for the first U, you could call it 1 plus tan x. Just try it out. And part of the reason I'm saying that is because I know, for example, that the derivative of cosine is negative sine x. And I just don't see how that's going to help us. When we do, if U was cosine, then du would be negative sine x dx. I just don't know how that would help us, seeing as how we have tan here, etc., etc. Okay, so I'm thinking let's start with calling U 1 plus tan x. So therefore, du is going to be, now, if you look at your reference guide on your trigonometric, derivative reference guide thing, it is the case that the derivative of tan x is secant squared x dx. Now, you might be wondering, okay, well, how does that help? Right? Well, it actually does help because secant is the reciprocal trig function to cosine. Now, what that means is if I multiply secant times cosine, it becomes 1. That is literally the sort of definition of a reciprocal, is that it's the number that when you multiply it by the other number, it becomes 1. Well, cosine is a reciprocal to secant, and therefore cosine squared and secant squared are reciprocals, which means if you multiply them together, you could say they will cancel each other and become a 1. Okay, they will cancel each other. Now, let's see that in action, because I'm talking a big game, but how does that translate to the actual problem? Well, first, we're going to go ahead and do this thing, where we just get the dx by itself. Probably the least confusing way to go about these. And you just trust the process. Dx is here. Although, we could also have put the dx down here. I'm going to put it over here because it could be there. All right. And we're going to replace this with a 1. It's going to be a 1 up there. So we're going to have 1 with the dx hanging out here. And I'm going to even wrap parentheses around it to remind us that it's going to be dx times this whole thing, right? So, on the next line, we have our notation. We have 1. We have cosine squared x. We have the square root of u. And then instead of writing dx, I'm going to write this, du times secant squared x. I'm going to keep it in parentheses. Du over, I should say, secant squared x. Okay? So this du is going to go across up top. Now this secant squared x is going to multiply times the cosine squared x, and it will cancel. Okay? In case that's still not clear, think about it. Cosine x is cosine x. Secant x is 1 over cosine x. That's something that you need to know. So do you see how this times this would cancel? And we'd be left with just a 1. All right? Very important that you understand that. So it stands to reason that secant squared times cosine squared would equal 1 as well. Now, if you want to work that out on your own, you could always do that. But that's true. So ultimately, we're going to have this. Okay. Now, you might be used to the du being off to the side. I could have written it off to the side, but whatever. We're going to put it up top for now. So, the reality of what we're working with at this point is, you know, u to the negative 1/2 du, okay? Because square root of u is really u to the 1/2, and then I could bring it up top to make it negative 1/2. At that point, we're ready to use the power rule. It will be u to the positive 1/2 all over 1/2 plus c. At that point, I believe we can replace our u with 1 plus tan x, keeping in mind it's still raised to the 1/2. Now let's get this over with. Anytime you divide by 1/2, it's the same as multiplying by 2. So it would be 2 times that plus c. Now in case that wasn't clear, remember you could flip that upside down and multiply, because a number divided by a fraction is the same thing as that number times the reciprocal of that fraction. The reciprocal of 1/2 is 2. So really, when I divide u by 1/2, it's the same as multiplying u by 2 over 1, which is just 2. To make it look a little nicer, we might want to do this. And that should be the answer. Now, to nitpick, you might want to extend that, and sometimes teachers like to do that to make sure it's very clear that the tan x is included. So that is how you do 43. Okay, so my student only asked me for 48, but I wanted to talk about 47 because these are also, these are both related to each other, because what you're being asked to do is find the derivative of an integral. You're trying to find the derivative of an integral. Now you might be thinking, okay, well, it's just opposite operations, so, or inverse operations, so shouldn't you just get back the original thing? Well, kinda. It depends on the bounds. It depends on the bounds, okay? Now, when is the case that you go from a constant to x, then actually yes, okay? This one, because it starts from 1 and goes up to x, when you take the derivative of this thing, you actually will maintain the expression, the function itself, only going to replace t with an x, which is pretty awesome. Pretty awesome. 2 plus x to the 4th raised to the 5th. Boom! How easy is that? Now remember, you can do that only when you go from a constant up to x. Okay? You just rewrite it, derivative, rewrite it, replace t with x. Now, you might be wondering, well, what would have happened? You know, still looking at problem number 47. You might be wondering, what would have happened if it was instead perhaps g of x equals the integral such that the lower bound was x and the upper bound was the constant 1. Well, the good news is it would be a very similar situation. Very similar situation, except you'd have to flip these first. You'd have to make it look like this. But in order to flip them, you have to put a negative in front. Okay? So you could flip it, but you just got to put that negative in front. Everything else would stay the same. And then you would go through the exact same process, only it would be negative 2 plus x to the 4th raised to the 5th. Now, the reason I bring that up is because that is a baby step scenario to this scenario, because this scenario does have the variable at the lower bound and a constant at the upper bound. So there will be some flipping action that we have to do, but we are going to have an additional problem. The additional problem is the fact that we have 1 over x squared. It's not just x over here. Now, we're going to deal with the fact that this is not just x soon, okay? First thing we got to do is flip it, okay? We're going to flip the whole thing. Now, remember, when we flip it, we're going to put the negative in front. Now, why are we flipping it? We're flipping it because we want the variable to be up top. That's why. So up here, it will be 1 over x squared. And then we still have sine of t cubed dt. So we've accomplished the first thing we need to do with regards to this situation. You're going to want that variable up top, even if it means putting that negative out front. Now, at this point, what we're going to be doing is imagining that there was another function, let's call it h of x, that was the exact same thing, only it was easy. We had x up there instead. And what we could do then is just go through the motions of what we typically would when it comes to finding the derivative of this. Okay, so as you recall, it would be such that we keep everything exactly as is, except we'd be replacing the t with an x. So it could not get easier to set this up. And of course, we are remembering to have the negative out front. We have the negative because we had flipped things earlier, so there is that negative that's out there. Okay, now, what do you do from here? Because they're not asking for this, they're asking for the derivative of this, right? Well, the good news is we can now use the chain rule. Let's keep in mind that g of x is actually equal to h of 1 over x squared, okay? So it's important that my student at home understands that part for sure. G of x, this, is the same thing as this, is the same thing as h of x, except instead of x, there's a 1 over x squared. Instead of this x, there's a 1 over x squared. Instead of this x, there's a 1 over x squared, right? If we replace this x with a 3, there'd be a 3 up there, right? So g of x is equal to h of 1 over x squared. That is the scenario that we set up here, okay? That's the scenario we set up between these two. So it stands to reason that g prime of x, aka the derivative of g of x, well, that's going to be the derivative of this. Except you can't just do that. You have to do the chain rule, okay? You have to take the derivative of this, and then you have to do the derivative of what's inside there, okay? That's the chain rule. Sure, it's the derivative here, but then it's going to be multiplied times the derivative of what's inside there. Well, the question is, what is the derivative of, 1 over x squared? What is that? Well, 1 over x squared is really equal to negative, or rather x to the negative 2. So if we were to use the power rule, the derivative of that would be negative 2 x to the negative 3. And that's really just equal to negative 2 over x cubed, which is right there. Okay? So that's the derivative of 1 over x squared. It's that. So that's what we have to multiply this by, because that's the chain rule. So you might be wondering, okay, great, but what the heck is this? Well, we already found it. It's this, only replacing x with 1 over x squared. So it would be the same thing as this, because this is the derivative of h of x, only it's the derivative of h of 1 over x squared. So we're just going to replace this x with a 1 over x squared. We're just going to replace this x with a 1 over x squared. So let's do that now. Equals, and I'll use some parentheses there. Now remember, the derivative of h of x was this. So we're going to replace it with, we're going to substitute in negative sign cubed of 1 over x squared. And that is still being multiplied times that. So that's going to be negative 2 over x cubed. Now, we have a negative times a negative, so the whole thing is going to be positive. I'm going to write it over here. And we have a sine cubed of 1 over x squared. We have this 2 that's in the numerator, so I'm going to put that out front actually. 2. That's all over x cubed down below. So this is a fraction, right? Negative 2 over x cubed. Or you can think of it as negative 2 over x cubed. This is not a fraction. This is negative sine cubed of 1 over x squared. There's actually a little 1 underneath there. So when you multiply straight across, it's going to become this. And that is the answer. A little bit of a process right there. I'd like to recap that. Okay, we're going to recap it. What did we do? Well, first we recognized the variable was in the lower bound, so that's already a problem. We have to flip it. So we did. We immediately flipped it and we put a negative in front. So boom, at least we took care of that part. Then we just imagined, what if there was another function called h of x, and we just had an x up here, right? Just a regular old x instead of 1 over x squared. And what if we found the derivative of that based off of the prior principles, where all you have to do is just keep it, right? We do have a negative out front, but we keep it and simply replace t with x. So in that moment, we constructed a new helpful function, and then we found the derivative of it. Then we recognized, we reminded ourselves that g of x, well, it's the same thing as h of x, except it's h of 1 over x squared. It's the same thing as h of x, except instead of x, there's 1 over x squared. I mean, clearly, right? This whole thing matches this, except instead of x, it's 1 over x squared. So another way of saying that is that g of x is equal to h of 1 over x squared. Then we realized, well, the ultimate goal is to find the derivative of g of x, right? That's the ultimate goal. So you could find the derivative of g of x by doing g prime of x. Well, that equals h prime of 1 over x squared. Except this is a chain rule situation because there's some stuff in there. So we have to do the additional step of finding the derivative of 1 over x squared, which we did. It's negative 2 over x cubed. So then that's our goal. The answer is h prime of 1 over x squared times this new negative 2 over x cubed. That's the answer. But what is h prime of 1 over x squared? Well, it's the same thing as h prime of x, except instead of x, we're putting 1 over x squared, right? Instead of x, we're going to put 1 over x squared. So that's what we did. We wrote negative sine cubed of 1 over x squared. There it is. So this became that. Let's kind of highlight that fact. We're going to highlight that with green. Now this part is that part. Pause the video if need be to make sense of that. This we just brought down. And then at that point, we could just multiply straight across. The truth is there's an invisible 1 underneath. You multiply straight across, you're going to get 2 sine cubed of 1 over x squared, all over x cubed, because there's 1 times x cubed down there. You have a negative times a negative, so the whole thing becomes positive. So that's the process. Obviously, practicing it would be key. Practicing it would be key. Now, I just checked my student's answer sheet, and according to the professor, the answer is 2 over x cubed times sine cubed of 1 over x squared. Now, if you look closely, that is the same thing. These are the same. All right. So for my student at home, that last one was a bit crazy. I totally get it. My strong suggestion is to do it again, only without looking at the answer. Do it again from start to finish. maybe even do it 2 to 3 times with no help. In my opinion, that's the way to get this one. Okay? And just stay calm and just practice it. Literally practice the same problem over and over until you get it right 3 times in a row with no help. I guarantee if you do that, when this shows up on the quiz or test, you're going to get it right. I guarantee it. All right. So anyway, hopefully that's helpful for my student and for maybe others. If you have any questions, let me know in the comments. And if I made a mistake, I don't think I did, but if I made a mistake, let me know. If you have a better way of doing things, you could provide suggestions. I may or may not go with them, but, I'm always open to learning for sure. So good luck, everybody, and I will talk to you next time. Take care.